Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to introduce the concept of the definite integral. At the end of the last video, we introduced the infinite Riemann sum and showed how, or mentioned how, that told us the area here. And effectively, the reason that works is because we're taking this approximation that was this area plus this area plus this area, and we're simply shrinking down these rectangles so that each one of these is the size of a single point. And then we're summing up those points, right? Those lines along the way, which, as I say here, is exactly how we determine an area anyways. We take a line, we multiply it by the distance across the edge of the shape. The problem here is that we've got this funky edge here that we have to deal with, right? And so that's what our sum is doing. Now, what our definite integral does is it simply tells us that that's what we're doing, is that we're taking this limit here. It's a notation in the same way that we had the d dx as our notation for saying that we're going to be taking a derivative. This integral tells us that we're going to be taking this infinite limit of a sum, which is the reason why we have this elongated S shape. It's telling us that this is an infinite summation from one point to another point. And the reason we call it a definite integral is because we know that we start somewhere and we end somewhere. We're not just going to be running off forever, okay? One thing we didn't mention in the previous video is that we're looking at all of these summations as being above the curve, but if your graph goes below the curve, you'll actually end up with negative values. So when we're talking about these summations or this integral, this is actually the net area. So if you do have a part of this graph that goes below, that will subtract. So you can actually end up having a total area that's zero if, for example, you had a graph that was symmetric above and below the line. We'll see examples of that later. Now, when we're looking at this, though, one of the things that we need to understand here is how exactly would we handle this idea, right? Previously, we looked at how we would take that limit, we could evaluate the limit, and then that allowed us to do a derivative. And in this situation, we're going to do something similar. But the problem is we're evaluating a limit of a sum. And when we're taking an infinite sum, that requires some skills that we maybe have not yet quite developed. And in fact, we're going to be looking at these ideas of infinite sums later in calculus because they do require some skills and some abilities that we're going to be developing throughout the rest of this course when we get to that point. So there are a few that we do know how to do, though, and that you have probably seen when you looked at, say, geometric series in your Geometry or Algebra 2 courses. So we're going to be looking at those. So what we're going to do in this video is look at how can we convert from the definite integral over to a Riemann sum that we might then be able to evaluate. And the way we do that is we notice that this x sub I and this Riemann sum looks a little bit like our right-hand summation, except that we're not taking the sample point from the right end, we're taking it from maybe somewhere inside that interval. And so when we're doing that, that right-hand sum is as if we took from A and then the interval being right at the edge. So the Riemann sum is that same idea, except that the interval, instead of it being right at the edge, is simply somewhere inside. So that's what we do. We simply say that that x sub I that we're putting in here, we imagine we're starting at A, and then we're coming in by whatever that interval is. And that's going to be where we take our point. So we simply do that. We go, okay, we'll start at A, and then we'll come in by whatever that interval is, however many times we need to. So for example, our first point will be this interval in. And then we'll come in by exactly that same amount of interval, and that'll put us here. So if our interval put us in the middle, for example, that would be the middle, and then we'll come into the middle, and then the middle, and then the middle, just like we did in the last video. Okay? So I'll demonstrate how this works next. So there's two things I want to talk about here. The first bit is a little bit of vocabulary. And all we're really talking about here is that if the limit of the Riemann sum exists on the closed interval, and remember, with definite integrals, we're talking about closed intervals, then we say that the function is integrable on that interval. Now, that's a little bit of a mouthful, so oftentimes we'll just say we can take the integral on that interval. But basically what this means is that this is the integrand. Just like before we say that we could have the derivative, this is the integrand. Now, when we're talking about it, the a and the b are the limits of integration, and we call the a the lower limit and the b the upper limit because of where we put the a and b on that s symbol that we use for integration. So in order to do this, we want to be able to take that limit just like we did when we were talking about derivative calculus. The only problem is that because we're taking the limit of a sum, it does throw a little bit of a wrench into the works. Now, luckily, we are going to learn some methods that make use of that antiderivative relationship that we were looking at. But for now, it is very important that we do understand how this relationship back to that summation works. So we're going to first learn how we can convert our definite integral back into the Riemann sum. And in order to do that, we simply need to identify the pieces and then put them back into the Riemann sum where they belong. And we're also going to look later at how we can do it the other way, but honestly, if you can do it one way, you can do it the other. So we just find our lower bound and our upper bound, that'd be our a and our b, and from those we can easily get our delta x. Now, because we're talking about integration, our n is just going to be an n because this is going to go to infinity. Right? So we keep it as an n. But remember, this is a constant. This is not a variable, okay? And that's going to be important when we're talking about later. And then our x sub I, we simply plug in the a, which in this case was 0, and then that delta x we found with the I. The I is our variable, okay? So we have the I and then the 3 over n. And then, of course, we have our f of x, which was x cubed minus 6x. Throw all of that into our Riemann sum, and we get this big nasty mess that we're going to have to do a bunch of algebra to. Now, when we're working with our sums, hopefully you remember some of the basic properties, which is effectively that we can move them around because it's all addition. And so we're going to go ahead and evaluate with our cube up here. And that's going to give us the 27 over n cubed, I cubed. And because of this being a constant, we can take that out of our sum, just like we did this 3 over n. So the 3 over n came out, and then we're going to be able to take the 27 over n cubed and the 18 over n out, and that will give us a sum here and a sum here. And so ultimately, we're going to end up with this limit and these sums. And our goal here is going to be to bring this limit through. Now, the problem is, if we were to try to bring this limit through now, it looks like we're going to get a 0 here, but that's not really what happens because we don't really know what's happening here. So in order to evaluate this, we need to know how do we evaluate this sum and this sum. And you might remember how to evaluate this sum. That one's a pretty easy one that you learn in Algebra 2. This one you may or may not know. So we're going to look at a few of these and also just kind of refresh ourselves on the rules for sums next. So that first formula might look familiar. That's just the first in integers. You probably learned that in geometry or Algebra 2. Now, the second one here is the first in squares. Again, that might be one you've seen, maybe not, who knows, but it is pretty common. The next one is one that not a lot of people have seen, but it is still pretty common and very useful, and it's the first in cubes. And between these, we can deal with most of the early polynomials, but the thing is, you'll notice that they get kind of complicated, and that makes things a little bit rough. Also, we don't really have a way of dealing with things like, for example, trigonometric functions. I've also put the properties up here so that you can work with those. But using these, we can generally deal with any of our definite integrals that are going to require polynomials. So let's go ahead and see how this would apply. Now, I think on the previous one I put 64 here. It's supposed to be 54, so I've corrected it here. But anyways, because we have an I cubed and an I, we can go ahead and apply our first n integers and our first n cubes, and that gets us n times n plus 1 over 2 squared and n times n plus 1 over 2. So just evaluating those a little bit, we notice that we have an n to the fourth and an n squared, so we simplify that, bring the 4 over, bring the n over, and then we can bring that squared back out, and that's how we get from here to here. And then we notice that we have a 1 plus 1 over n. So when we take the limit as n goes to infinity, this part will become 0. We learned that back with our derivative calculus. And so we're just going to get 81 over 4. And then similarly over here, we've got n squared, which is going to go ahead and cancel out this n nicely, and then we're going to get 1 plus 1 over n. And again, when we take that limit, this part's going to become 0, and so we're going to get 81 over 4 minus 27, and we get a nice negative 6.75. So you might wonder, why was that negative? But if we go look back over at the graph, we can see that that's because we start at 0, we dip down, and then we rise up. So if we had taken this definite integral from, say, 0 to 4 or 5, this would have been a positive value. But because we had that initial negative amount, yeah, our net area is a negative value. And that's one thing that is important for these, is that when we're dealing with derivatives and integrals, we are kind of working with signed quantities, which typically we're going to be dealing with vector quantities. So we do want to make sure that we understand kind of what the numbers mean in context, because just because it's a negative doesn't mean it's a bad quantity. You know, maybe negative means south, maybe it's a directional value. Who knows? It'll all depend on, the kind of context of the problem. So what we're going to do next is I'm going to give you a couple of problems for you to practice converting from an integral to a Riemann sum, and a Riemann sum back to an integral. And then in the next video, we're going to look at some of the properties of our definite integrals before we look at ways that we can work with the integrals that are going to be hopefully a little bit less involved than having to constantly work with these infinite sums in this manner. So I hope you found this introduction to the definite integral helpful. If you have any questions, you can drop into the comments below or join us on Discord. And as usual, the answers to the exercises will be after the outro.